Hello and welcome to Autology, the weekly podcast that brings you the latest on automotive technology. This week's episode is called Steeling Ourselves for Supply Chain Shortages. Is electrical steel next? And you're here with me, Graham Evans, Director in the Auto Supply Chain Technology team at IHS Markit, and Zach Leatherston, President and Managing Director of XEL Mobility, alongside Claudio Vittori, Senior Research Analyst, E-Mobility at IHS Markit. Gentlemen, welcome.
Thank you for having us.
Right, thank you for joining this week's episode of Autology. So before we dive into the subject matter, maybe a brief introduction. I think whilst Claudio is known to the audience as an IHS Markit analyst and is familiar to many of you, maybe Zach, if you could give a little bit of an introduction and talk about your role, your background, and a bit about what XEL Mobility does.
Sure, thanks, Graham. So XEL Mobility is a consultancy I founded that helps organizations proactively navigate the impact of disruptive megatrends within their businesses. We look at some of the megatrends, especially in the transportation industry around autonomy and electrification. While they're part of transportation, they sort of function fundamentally different than the automotive or transportation industry traditionally has. And I've sort of noticed there's a niche there for companies that are looking for advisory services to figure out how to successfully enter those markets or navigate profitable growth once in them. So the projects I work on generally involve some combination of strategy, engineering, market analysis, operations, and business development. We have specific expertise in kind of the transportation e-mobility domain, and more specifically traction motor and traction motor components. There's a lot of focus on the battery supply chain and not nearly as much on the traction motor side within automotive, and we're kind of filling in that gap.
Fantastic, and a suitable segue, I think, to today's topic, given that, yes, you're right. We talk quite a bit about batteries on Autology and not so much about motors, but I think, critical to the development, the evolution of the electric vehicle and its, if you like, population in mass market uptake. So I think what we want to discuss today really is around whether we see a shortage of this critical material on the horizon. Naturally, with the monumental impact that the semiconductor shortage has had on industry output in the last 18 months or so, people are looking over their shoulder for what the next big supply chain risk is. I mean, we saw announced just yesterday that GM has announced sales in Q4 in the US were down 43% year on year, pretty much exclusively attributed to the semiconductor shortage, and they're not alone. So it seems a sensible time to reassess, the wider supply chain risk associated with the content of vehicles that are planned to come to market in the next couple of years. So maybe just to frame the discussion then about electrical steel and its importance, then it would be great if we could just have a brief overview of what is electrical steel, how it differs from conventional steel, and what the various types are. And perhaps it might also be worth at this stage framing the different industrial applications. So maybe Zach, could you kick us off?
Sure. So electrical steel is sort of one of the sort of commodities that's in the steel market that most people have never heard of, but actually holds a significant importance within our everyday lives. I think if we take a step back, I think it's first important to talk about what is an electric motor. An electric motor is a device which converts electrical energy into mechanical energy. And electrical steel is essentially at the heart of that device to efficiently create a magnetic field. When we talk about steels, traditionally we think about mechanical characteristics being important. And in the course of electrical steel, while mechanical characteristics matter, the bigger focus is on electromagnetic characteristics. And there are really, a couple critical characteristics within electrical steel that are important for performance. One is core loss, which essentially looks at the efficiency of the steel in converting electrical energy to magnetic energy. Essentially, it's a function of the energy input that's lost as heat instead of being into generating a magnetic field. And then there is magnetic induction or permeability, which essentially focuses on the amount of magnetization which can occur in a specific area within the steel. And these two characteristics drive the efficiency and the torque or power output of the motor. I think one thing which sometimes gets overlooked is, depending on the market study that you look at, anywhere between 40 and 60% of the electricity in the world is consumed by electric motors. And these rotors and stators, which are comprised of electrical steel, are one of the 2 or 3 items which in the motor, which are critical to defining the performance. So it's a big deal in our world today and for the environment, even though it's not a product many people are familiar with. So we looked within the domain of electrical steel. There's really 2 major types. One is non-oriented electrical steel, and the other is grain-oriented. And the difference there kind of gets back to the crystallographic structure of the grains themselves. Non-oriented electrical steels have magnetic characteristics which are optimized in all directions on the material on the magnetic plane, whereas grain-oriented focuses on optimizing the magnetics in one direction. So the non-oriented electrical steels tend to be used for electrical rotating machinery like motors and generators, whereas the grain-oriented steels tend to be used in non-rotating equipment like transformers that are used in the power grid. For relative scale, the non-oriented market in 2020 was somewhere between 11 to 12 million tons, and the grain-oriented market was 2 to 2.5 million tons. So still very, very small in the context of the global steel market. And then, the focus of this article is XEV grade non-oriented. This is really a unique subset of the non-oriented materials. And these are steels that are designed specifically for the requirements of traction motors. And that in order to optimize performance at those operating points that traction motors traditionally operate at, you're looking at unique chemistries, processing methods, and thicknesses. So they're really the most highly engineered and complex of the non-oriented electrical steel family.
Okay, fantastic. So, I think you make the point well that this represents quite a specific segment of what is a familiar, industrial quantity, a familiar industrial material. And from a market perspective, considering the forecast growth of electric vehicles, maybe Claudio, you could give some context to how much we therefore expect the demand for XEV grade non-orientated electrical steel to increase.
Yes, of course. Thanks, Graham. Let's say, as anticipated by Zach, the electrical steel and the XEV's grain or non-grain-oriented electrical steel represent a tiny portion of the overall global steel market. We are talking about less than 0.5 millions of tons within a market which crossed the 2 billions of tons as a global steel market. And this part of electrical steel refers mainly to the traction motors. So these exclude all the motors regarding, for example, the windows, electrical motors for windows. And the amount of electrical steel of XEV's non-grain-oriented electrical steel refers mainly to the power output of the electrical motors. And if we consider, for example, plug-in hybrid vehicles with power output in the range of 30-50 kilowatt, the amount of electrical steel required is in the range of 20 kilos. Of course, the more we grow in terms of power, the higher is the quantity of electrical steel required. If we go into a pure electric vehicle in the range of 200-300 kilowatt max power output, then the total requirement of electrical steel goes up to 60-70 kilos. So of course, in the near future, the fact that the electrification process is going ahead and is going faster towards electrical vehicles rather than mild hybrid and plug-in ones, the market is expected to increase rapidly. And already in 2026, we expect a market of non-grain electrical steel of more than 2.5 millions, which is expected to cross the 4 millions of tons by 2030 or after 2030. And as I said, I mean, this refers only to the propulsion motor, and this refers only to the passenger vehicle markets. If we sum up all the other combination, and if we sum up the possible demand arising from other sectors, of course, the overall market may grow rapidly and over the figures that we have mentioned now.
Fantastic. Okay, so understood. I mean, it's again a specific segment of the market, and of course, performance requirements on the EV are going to dictate how much is required. I mean, for us to be concerned now that there's a potential shortage, this kind of implies that this ramp up in electric vehicles was somehow not expected or not planned for. Could you maybe comment, Zach, on what's changed? You know, why are we concerned now, given the status of the market at the moment?
Yeah, I think what's changed now is the magnitude of the demand ramp up for hybrid and electric vehicles that's occurred in a relatively short-term planning horizon as it relates to the planning horizon for steel mills adding capacity. You know, I think it's also important to note a lot of steel mills installed specialized capacity over 10 years ago to produce XEV grade non-oriented electrical steels, because the electrification of the automobile was happening imminently. And then the year after that, it was happening imminently, et cetera. And, you know, frankly, outside of Japan, up until last year, capacity utilization on most of these lines was very, very low. You know, steel making is an incredibly capital intensive business. You can't just add small amounts of capacity to produce these XEV grade steels. It's kind of the equivalent. I'll draw the analogy. It's like if an automaker putting in a steel mill to produce these types of steels is essentially the equivalent of an automaker only being able to start up a factory that can produce 1 million vehicles. It's something that's almost impossible to inch into and to have a cost competitive or a competitive cost structure. So that's part of the challenge. You know, the other challenge is just the time it takes to build. You know, you've got roughly 2 years from when the shovel enters the ground to the completion of construction, but generally there's at least 1 year of solid full-time engineering work that's required before that. And then when you start getting into capital expenditures that are hundreds of millions of dollars, there are of course approval processes, which, you know, generally can add another 1 to 3 years onto that. Then when you factor, okay, we have a mill that's capable of producing the steels, in a lot of cases, there's still debugging and engineering development work, which has to be done to develop the grade. So, I mean, you know, frankly, we know today essentially what available capacities will be in 2025 because of the lead time for these mills to add complexity. So I think that's, you know, that's sort of the crux here is the timing that the OEMs are ramping up volumes is much shorter than the 3-year planning horizon of steel mills, and now the steel mills need to catch up. You know, I think it's also important to note that there's not a lot of players in this XEV grade non-oriented electrical steel market. You know, there's only maybe 14 steel mills globally that are capable of producing these grades, and not all capacity is created equal. You know, in a lot of cases, there's only one mill capable of meeting an OEM's specific requirements. You know, there's an interesting story that's gotten some press lately about Toyota and Nippon and Bao. Toyota has traditionally worked with Nippon as their electrical steel supplier. Nippon was a Keiretsu supplier who was involved in the initial launch of the Prius. You know, Nippon is nearing capacity, and Toyota has had a strategic initiative to try and bring on other suppliers. And it took them almost 2 years to qualify Bao Steel as a supplier. So the largest supplier of electrical steel in the world, who has extensive R&D capabilities, it took them 2 years with Toyota's support to meet the specifications that Toyota has. shortly after they did that, Nippon ended up suing both BAO and Toyota for patent infringement related to the Nippon electrical steel production process. So, there's other complexities within here as well that, when you look at capacity at a macro level, you have to be careful because available capacity at a macro level doesn't always translate to microscopic supply chain reliability. I think one of the other things which is important to note is, almost 90% of the capacity for these XEV grade steels is Asia, and it's China, Japan, Taiwan, and Korea. These are countries that have fairly nationalistic attitudes embedded within their business cultures. And, there's going to be a sort of a default position of when capacity starts to get tight, of serving their local customers first, which again, I think puts some risk into the supply chain, especially for companies operating outside of Asia. The other piece that's challenging here is there's some unique capital equipment which is required to produce these XEV grade non-oriented electrical steels. There is some swing capacity, which is what I'll refer to as variable capacity that mills can allocate to different products. But generally speaking, for electrical steels, especially XEV grade, it tends to be relatively small because the processing techniques require some unique equipment that really isn't used in other types of steels. And this is just focusing sort of at the steel mill level as we sort of move through the supply chain. I think there's other risks that occur with the motor core stampers who are converting the electrical steel into rotor and stator cores in terms of capacity at that level, as well as concerns with the capital equipment they need to produce the rotor and stator cores and the tooling. They're all sort of unique and discrete core competencies within their subsets, similar to XEV grade non-oriented within the non-oriented steel market.
Yeah, fascinating stuff. I think that we often just appreciate the end component here, or most people have a perception of what the motor will be, but of course the equipment to make the motor could also be just as equally the bottleneck. Thanks a lot for that. Maybe Claudio, on the vehicle side, then, of course, IHS Markit has an electric vehicle forecast. We have a view on how quickly we think electric vehicles will come to market. But of course, when the prevailing macroeconomic or regulatory environment changes, this causes us to reflect on the forecast. And maybe you could give an overview of how our view has evolved in light of recent events and recent changes in the wider macroeconomic environment.
Yes, of course. I mean, of course, as IHS Markit, we do forecast. The electrification is impacting our forecast in terms of passenger vehicle market, and electrification is becoming a game changer across the board. All the sectors. And if we look back at the history, we do see our expectation about electric vehicles has changed and is still changing. Is still impacting massively the overall figures until 2030 and beyond. And there are, a few things that are, constructively pushing this direction is the commitment, the positive commitment of the OEMs towards electrification, especially towards pure electric vehicle technology rather than the plug-in ones, together with the consumer acceptance and the positive response of the consumers towards the adoption of electric vehicles, despite all the bottlenecks still in place, as the charging infrastructure, for example. And these, together with the always stringent regulation on passenger vehicle market, is one of the reasons why the electrification is growing, and one of the reasons why the electrical steel is positive on one risk in the future. More than everything, in the components domain, there is a topic that I will try to raise today, is the fact that the electric vehicles is growing faster than all the other technologies, brings together another topic, that is the multi-motors equipment into the vehicles, especially into the high performance car, but not only the high performance car. The amount of motors can be 2 times, 3 times, or 4 times the amount of vehicles. And if you look at the components or overall volumes, in 2030, we are expecting, a higher demand of components, higher demand of motors than the expectation about vehicles, which is, which pose another question, another point towards the possible risk of shortage into electrical steel domain.
Yeah, I think you've raised an interesting point, Claudio, and it sort of touches on something, Graham, you led off with about the semiconductor industry. The interesting parallel to me, or non-parallel, is, in the semiconductor space, there's certainly growth and demand, but not from a percentage compound annual growth rate like you're seeing in these types of components for electric motors and thus electrical steel. So you're talking about needing to add huge amounts of capacity relative to what's already there on the base. And in a lot of cases, you're asking companies which have traditionally not participated within the automotive supply chain to now start supplying critical automotive powertrain technology. Even within some of these, the steel mills, while the mills themselves may participate heavily within automotive, the divisions which have traditionally supplied electrical steel have not. And, so there's a difference in terms of just operating rigor, which is required to be successful. And so I think, you've got a situation here where you're talking about, for many companies, a pivot into a new industry on top of huge growth. So, I think those two challenges, do make this a little bit unique from the semiconductor situation, although I still do think it's a valid parallel. I think the other thing too here is, we've touched on this XEV grade non-oriented electrical steel and how complex it is. I used to, 3 or 4 years ago, I used to call this market the 1% of the 1%. Electrical steel was 1% of the global steel market, and these XEV grades were 1% of that. And, now it's maybe 1%, 2.5% of the 1% or something like that, but it's still an incredibly small market. There's highly concentrated engineering and R&D expertise. There's lots of intellectual property. So this is not an easy move, even for companies that are producing commodity grade non-oriented electrical steels today. It's not a situation where they can just go out and purchase a cold mill set up for these XEV grade non-oriented electrical steels, turn it on and be successful. There's going to be a significant learning curve of many years, even for those companies.
Yeah, thanks a lot. I think this, even though it feels like a 1% of a 1% or a very small amount, I guess obviously, demand for electric vehicles in comparison to, steel for construction, of course, is tiny. But of course, we're staking a huge amount of the future of CO2 reduction and emissions improvements and environmental benefit on this transition to electrification. So it's such a critical small piece, shall we say. Maybe in terms of the risk, if we try and divide this out, let's subdivide it out perhaps in terms of the short-term risk and the medium-term risk. Maybe Zach, you could comment. I mean, is there enough capacity to see us through the next, the next few years, the next couple of years?
That's Graham, it's a challenging question to answer because the macro capacity doesn't always translate to the micro capacity, as we talked about. I think 2022 we should be okay. 2023, I think there is some potential for some very, very, very tight capacity. I think it'll be a bit of a tightrope trying to walk through it, but I think it's possible. But 2024 onward is where, for me, things really start to become a bit more tenuous, because it's going to be reliant on how quickly the steel mills can bring the capacity online that they've already announced. And I think with the ongoing challenges associated with COVID and the lingering pandemic, construction and engineering activities tend to get slowed down. And so while they've stated dates, it's very likely they may not hit those dates because of some of these extraordinary events going on in the world today. and that could create some challenges.
Understood. Okay. I mean, maybe from Claudio, from the automotive perspective, a few comments there to add to what Zach said, and thinking about what's happened with electric vehicle sales, perhaps in comparison to general internal combustion engine vehicle sales, and the plans of the OEMs and the impact of the chip shortage.
Well, I think Zach point, I mean, we have to be very careful about electrical steel, because if you look back in the last months, 18, 24 months, we can see how the automotive industry faced a lot of issues in terms of, different issues impacting the overall production volumes, especially the chip shortage, which I think accounted until today up to about 10 millions of units lost just due to the chip shortage. So we have to be very careful about electrical steel, because more than everything, there might be a risk, and this risk can effectively be an important factor for the future production of electric vehicles. Despite several announcements that have been made, the risk is still there. I mean, we do see the risk. And in terms of general view, I used to describe the electrical steel market in a sort of two phases market until 2030, 2033. I think there will be a sort of, the 2022 seems to be a year where the demand will be fulfilled. If we look at the horizon until 2025, 2026, we define like a concern phase, where in principle the demand can be fulfilled because the production is okay, is in the right on track on supplying what will be demand by the OEMs. But of course the risk is behind the corner, because if external factors might occur, then the production can slow down a bit. Then we see the second phase, which is a possible structural shortage risk, which happens after 2025, 2026. Then if no big investments are gonna be made, I mean, the risk is important. And so we do see a risk in the second phase, while we do see the first phase until 2025, 2026 still secure if nothing specifically happens.
And I think just to put some context into that, if you were look at the 2020 numbers for demand for these XEV grade non-oriented electrical steels versus 2030, we're projecting a 10x increase. That's a huge number in any business, let alone one that is as capital intensive as steel making.
Absolutely, it's a really good point, and I think I like the point you made earlier, Zach, about the kind of the downstream supply issues, the availability of equipment, etc. And I mean, if we start to think more towards the medium term, then, and we think about what do we know of the steel suppliers' intentions, and if they can help meet some of this demand to come, and perhaps the associated infrastructure around helping those steel suppliers expand. Do you think it's feasible?
It's I think it's feasible, but it requires a lot of action, and a lot of action quickly. The projections that were made by IHS, Exxon Mobility, and Metals Technology Consulting take into account over $3.5 billion of announced capacity investments by mills to increase XEV grade non-oriented electrical steel. There's some other announcements which are also factored into the capacity analysis, which haven't been disclosed publicly yet. But even when we factor those in, there's still this significant structural deficit in the back half of the decade that Claudio referenced. So I think there is a very short period of time we have, really the next 6 to 12 months to solve some of these structural issues, or we could be running towards a ledge in the 2026, 2027 timeframe that may become challenging to not jump off of. We already talked too about the time it takes to bring that new steel production capacity online, and that's really where you start getting into these 3 to 5 year planning horizons, which are necessary. I think on the the adjacent businesses, there is probably only 20 companies globally that have the technical competency to convert the electrical steel into rotors and stators for these XEV requirements. It requires unique know-how, unique capital equipment, unique tooling technology, et cetera. It's essentially a discrete core competency from motor core manufacturing for industrial applications, or even for automotive auxiliary applications like window lift motor cores or power steering motor cores. These are businesses that have traditionally been less than 300 million in revenue. Most of them have been less than 200 million. They've been family-owned businesses and family-led businesses that have traditionally participated outside of automotive. So there's a big shift which is required within these businesses, and a need for huge capital investments to be able to support the growth at the motor core stamping level or lamination stamping level. And then when we start to look at the capital equipment, there's maybe 5 stamping press suppliers globally that can supply the types of presses that are needed to produce these XEV rotor and stator cores. Some of the ancillary stamping press line equipment, there's even less than 5. There's very unique tooling that's required to produce these parts as well. Some of these stamping dies can have over 700 components in them that make shape. Even if we do solve the situation at the steel level, there are serious risks elsewhere in the supply chain. And I think that's why you see companies like Schaeffler, making announcements about beginning to stamp laminations themselves, is because of some of these concerns that they have with the supply chain.
Got it. Okay. So, on one hand, quite scary when we think about the plans of OEMs coming up, but at the same time, some fantastic opportunities in there for people who want to expand, or people who want to grab a bit more of the value chain, if they can gear up and develop this capability in a short space of time. And maybe, Claudio, it's quite simplistic probably to say that, if we asked the question, who is most exposed here? Of course, people who make more electric vehicles are likely to be more exposed. But could you explain a little bit some of the analysis that we've done here and how we went about trying to understand who might be at most risk as a result of this potential shortage?
Yeah, of course, the correlation with the quantity of electric motors expected is the main driver of, the exposure of the OEMs towards the electrical steel, the risk of possible shortage in the electrical steel. I think overall there are 2 factors that we may take into consideration when we talk about risk or exposition or about the possible shortage. The first one is about, the volumes. And in terms of volumes, we do refer to the OEMs more exposed to pure electric vehicles rather than mild hybrid ones, because as we said previously, these are the vehicles where the concentration of electrical steel is higher, so the demand is higher. And if I look at, the situation is changing rapidly between today and 2030, because Tesla is, for example, today one of the main electrical steel. But if we look at 10 years horizon, some other players will pop up in the market in terms of volumes. That's the case, for example, of Volkswagen or Stellantis, so European groups, as well as Renault, Nissan, Mitsubishi group, with still Tesla remaining to the one of the major requiring electrical steel, and as it will happen for Toyota due to the large volumes required in 2030. And the other point is about the region-wise, because of course the quantity of motors, electrical steel is one of the points, but the other point is where you are going to produce, where you are going to manufacture your electric motors. in some regions, and that's the case, for example, for Europe and North America, the OEMs will face additional risk related to the competitiveness challenges resulting from tariffs or imported material fees. And where we do see for now the European market and North America, and the ones more affected by these two additional factors.
Yeah, I think Claudio, you've made some really good points, and I think the other OEMs which may potentially have some risk potentially are folks like GM and Ford, where they've traditionally made the vast majority of their profits on large pickup trucks. If there are shortages of electrical steel and they can't effectively convert pickup truck customers profitably to electric vehicles, electric pickup trucks, their risk could be quite high. There has been a lot of compliance vehicles traditionally sold in the North American market by these OEMs, essentially at very little to no profit, small cars to balance out average fuel efficiency for the pickup trucks. And so they're willing to make $500 on a small passenger car because they know it balances out the $12,000 they make on the pickup truck. And if, as the Biden administration has announced more stringent fuel efficiency legislation and greenhouse gas legislation in the US, if they can't get the motors in, it may force them to have to limit sales of pickup trucks or to artificially deflate pricing on vehicles that have better fuel efficiency, possibly selling at a loss just to meet the government regulation that's out there.
Yeah, it's a good point. It's certainly potentially going to affect product mix, I think, for OEMs. And obviously, when we look at OEM by OEM, their propulsion system strategy, shall we say, there's obvious there's evidence of OEMs more exposed. Certainly, I think we've done quite a lot of scaremongering here, perhaps, or quite a lot of analysis of what the problems are. Perhaps if we think about this a bit more optimistically about what the potential, what the options or what the potential solutions here. Maybe a few thoughts, Zach, on if you were sat on a large capital allocation now to go expand a company or develop a new company, or how would you suggest we go about overcoming this potential industry bottleneck?
I think it's going to require a lot of coordination throughout all levels of the supply chain. And I will say I have seen the supply chain within the e-mobility space of automotive functioning much more collaboratively than I have in the other subsegments of automotive that I've worked in. And I think that's because there is a recognition that this is new technology, and the subject matter expertise is still being developed, and that collaboration is necessary to work through the major challenges that are there. I think the first piece is the steel makers, working with them to make sure that the swing capacity that exists to produce, that's capable of producing XEV grade electrical steel that may currently be allocated to higher grade non-oriented, or in some cases grain oriented, seeing if it's possible to essentially lock that capacity up over the coming years. I think it's important when both OEMs and tier one traction motor manufacturers are designing motors that they be very cautious of how they develop material specifications to make sure that there are multiple mills that are options for sourcing. That's becoming particularly challenging because there is no global electrical steel producer in terms of having mills in multiple continents that can produce equivalent products. And as the automakers are rolling out global standard platforms, some of the nuances of material performance that's available, say, in China, that's not available locally from a European supplier is actually having them to go in and do some slight redesign work, even though technically it's a global standard platform where that shouldn't happen. There are some interesting opportunities to change some of the construction methods of the motors, which would potentially open up opportunities to reduce the planned design scrap. So when we produce a rotor and stator out of electrical steel, we're essentially stamping a circle out of a square, and you can end up with planned design scrap, which can be 30, 40, 50, in some cases, 70% of the gross material required to produce. So if there's opportunities to better utilize the steel in the design process, it may drive some more complexity in the motor assembly and construction process, but it's a trade-off which I think needs to be analyzed more thoroughly. One of the other big points is the thickness of the electrical steel. So as steel gets thinner, the magnetic performance tends to improve, especially when you have motors that are operating at high frequencies, which is where these traction motors operate. So there's been this huge trend within the traction motor space to go to thinner materials. 10 years ago, the default was 0.35 millimeter material. Now there's very little volume at 0.35. Most of it's in the 0.30 to 0.27 millimeter, and a lot of it, frankly, is at 0.25 or trending there quickly. And while 0.02 or 0.05 millimeters in thickness may not seem like a lot, from a percentage basis, if you look at the percentage thickness reduction, it's quite large, and that has a significant impact on the absolute tonnage output that a mill can have. Essentially, a steel mill can process the steel, the coil at X meters per minute of linear speed. It doesn't change all of that much with thickness. So when I reduce the thickness from 0.35 to 0.25, I've essentially taken almost a third of the capacity, absolute tonnage capacity, out from that mill. So there needs to be a balance of looking at the thinness of the steel versus the output of the motor, and maybe even a trend to start going back thicker. Also, there are some post-stamping or post-production technologies, thermal technologies that can be used on the rotor and stator, called stress relief annealing. It's essentially the inverse of a heat treat process. Instead of trying to induce mechanical strength in the material, we're actually trying to remove the embedded stresses, because mechanical stress degrades the performance of electrical steel. So these, this stress relief annealing technology can actually allow a thicker steel to perform like a thinner steel. So essentially, a motor designer that was using 0.27 millimeter without this post-stamping stress relief anneal could now utilize a core with 0.30 millimeter material laminations, go through the stress relief annealing process, and have equivalent performance. And I think particularly for the supercars and the high performance motors, possibly looking at the use of cobalt iron electrical steels. These have traditionally been used in aerospace applications, and there is a significant cost premium, but a huge performance improvement in these types of steels. So especially for high torque, high power performance vehicles, they could be an interesting option.
Okay, fantastic. So some good options for diversification, perhaps at the high end, and some ways to save money and save on material for mass production, certainly, to I think probably achieve the performance that we need. Maybe Claudio, a few more comments on your side.
Yeah, thanks, Graham. Let's say I think I have a positive answer and a negative answer. And from the technological point of view, I think unfortunately for now, we do not have any specific solution in terms of different topology of motor that might, exclude electrical steel requirement. Some OEMs are now, going in the direction of axial flux machine technology, which is not requiring XEVs, not grain-oriented electrical steel. As IHS Markit into the components domain, we are forecasting the electrical motor adoption and or at the nameplate level, and looking at 2030, despite some OEMs are going for this solution. That's a case of Renault Nissan, as well as already applied into some Stellantis into Ferrari application, as well as the important investments of Daimler into the technology. We do forecast until 2030 a limited use of this technology. We are in the range of few percentage points into the overall market. And these will mainly refer to hybrid solution, not covering some of some of the motors requiring the most of electrical steel, or in some some application really high performance car, due to the fact there are still some technological issues into the production and related to the cost of production of this technology. In the other side of the coin, I think there might be a mitigation plan in terms of a new position of OEMs get inspired by Tesla. So OEMs may seek to be vertically integrated into the overall supply chain, and of course it goes without saying that it's gonna be applied also into the motor supply chain, and perhaps directly partnering or teaming up with steel manufacturing to better control the inputs, and so indeed adopting a solution to mitigate the plan for the near future, especially into the long run. This process may happen, and as we see in the data, I mean, the in-house production of OEMs about electrical motor is growing as a percentage. We do expect that in 2030, 2/3 of the high power motors will be made in-house. So this gives us an indication about a possible mitigation plan already ongoing to the OEM side, especially into the positioning to the market rather than in different technical choices.
Yeah, I think, Claudio, you've raised some very good points again, and I think there could definitely be a situation where the OEMs start treating the traction motor supply chain like they have the battery supply chain, where they're making investments and forming partnerships at all levels. From the materials, and in the case of batteries, even some of the mines on up, to make sure that they have the security in the supply chain that they need.
Good stuff. Thanks a lot, and thanks for the context. I mean, regrettably, that's all we've got time for. Covered a lot of ground on a fascinating topic. A big thank you to you both for joining Autology today.
Thanks for having us.
Thank you.
And thank you to all of you listeners for tuning in as well. We'd love to hear your thoughts on today's podcast episode at our autology@ihsmarkit.com email. And you can find out much more at autotechinsight.ihsmarkit.com. Please don't forget to hit all the subscribe, follow, and like buttons to stay on track with the latest Autology podcasts. And we look forward to you joining us again in the next episode. Bye for now.